what we're starting with today is Pascal's triangle. So you guys might remember this from last year, but the whole idea with Pascal's triangle is we should be able to do ones down the entire side. 1, 1, 1, 1, 1, 1. And then down this side as well, 1, 1, 1, 1, 1. And then what we would do is we would add the numbers from the top two rows above to get the next number in. So this would be a 2, and then this is like 1 plus 2 equals 3, 2 plus 1 equals 3, 1 plus 3 equals 4, 3 plus 3 equals 6, 3 plus 1 equals 4. So that's what Pascal's triangle looks like. We're bringing that back this year. So for use in probabilities. What I'm going to ask you guys to do now is just go ahead and fill in the rest of this triangle for all the rows that I have so far. And we'll talk about the rows in a minute here. Okay, so once we have the Pascal's triangle calculated here, just a few reminders about it. So it starts up here with like row 0. And then it's like row 1, row 2, row 3, and this goes all the way down to row 9. So what can get a little confusing for some people is they start at row 1 at the very top and they think it's 1, 2, 3, 4, 5, 6, all the way down to 10. But that's actually not quite accurate. It's going to look more like this. And what Pascal's triangle tells us, it tells us the binomial coefficients. Now, we might remember this from last year. This was the very, very beginning of the year last year when we did the binomial theorem, which was not easy. You know, that's one of the harder concepts from math last year. And we're going to look kind of at it today, but I'm going to show you how to do a lot of these problems in your calculator. So hopefully that will be helpful when solving these types of problems. But just a reminder, binomial coefficients in row n plus 1. So what they do here instead of what I do is they start with row 1 up here, and then they count down to row 10, I think. The triangle represented by the following notation. No, it is. No, they do it the same way, so it is row 0. Okay, 0 to 1, 0 to n. Okay, good. And then we talked about combinations. Did we do combinations last year? Like P and C, where you do like C of n over r factorials. I think we did this last year. Just a quick reminder, when you see this, like n is the top number, so we'll say n is the number right there, and then r is going to be whatever number's in the bottom. So if we wanted to write this equation out, we would say 5 factorial divided by 2 factorial times 5 minus 2 factorial. And those factorials, that was at the exclamation point, and we would just do 5 times 4 times 3 times 2 times 1. Like you'd always go from that number down. And then 2 factorial is 2 times 1. 5 minus 2 becomes a 3 factorial, which is 3 times 2 times 1. And then what we would do is we would just go ahead and simplify this. So for example, I have the 3 times 2 times 1. I can get rid of all those. And then I have a 5 times 4 is 20 divided by 2 is 10. So if I were doing what I would call this is 5 choose 2 is the way I would say it. If I were doing something like that, then what I would do here is say 5 choose 2 is 10. And what that's doing is saying if I went down to row 5 in this column, okay, and then it says choose 2, which means I'm choosing the second number, which is weird because it's really the third spot in the column, 1, 2, 3. It'd be that 10 right there. That's what 5 choose 2 is, okay? That's where the 5 choose 2 comes from. All right, that's just a quick refresher on this. And we're going to have something that looks very similar to the binomial theorem today, and I'm going to talk about that. But before I do that, I'm going to get us into some groups. I'm going to put us in breakout groups today. Probably about 5 students per group. I'm going to need everyone to get themselves a coin. So, coin with heads and tails. So if you don't have one easily available, please see if you can find one real quickly. And what we're going to do is we're going to
use Siri to flip a coin for you.
What'd you say?
You can use Siri to flip a coin for you.
Are
can say,
you?
like,
Oh, Siri. Yeah. Yeah, just don't make up coin tosses. What I want you to do is I want you to do 6 coin tosses, and you're going to record your heads and tails for each one. And what we're going to do with our groups of 5, the reason I'm putting this in groups of 5, is I want everyone to do 6 coin tosses and then share your data with your group. Okay? And then we're going to do 10 total trials. So if you're in a group of 5, everyone will need to do it twice. So you'll do 6 coin tosses 2 separate times. And you're going to write it down. So like, for example, it could be heads, tails, heads, tails, tails, heads. Or it could be tails, heads, tails, 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 tails. All right? And then we're going to write down how many of your trials resulted in outcomes like this. So where you had 3 heads and 3 tails. How many of your trials resulted in where you had 5 tails and 1 heads out of your 10 total trials. And then discuss this claim. The probability of a total of 3 heads in 6 trials is more than the probability of a total of 1 head in 6 trials. Justify your answer. So I'm going to put you guys in groups to work on doing the 10 total trials and then answering these 2 questions afterwards. And again, don't make up numbers if you don't have a coin. Maybe you can use Siri to flip a coin for you, but do actual 6 coin flips. And then share your information with your group. Okay? Let's do this. All right, so get to your breakout rooms. I'll give you guys about 8 minutes on this, 8 to 10 minutes. Specifically, like, does anyone have any trials where they got all tails or all heads? Does anyone have any trials where they just did that? Okay. Did anyone have any trials where they got 5 tails or 5 heads? No?
I got 5 tails.
You have 5 tails? Cool. All right. Yeah, if you guys had anything like that, just hit it up in the chat or just let me know. So you have one group that had 5 tails. Okay. Anyone that had, let's see, anyone that had 4 tails or 4 heads? Hopefully quite a few of you. Okay, so we had one that had 5 heads, got it. Also 5 tails, got it. So we got a couple of those. Okay, 4 tails. Your whole group got 3 heads, 3 tails. Okay, good. So when we get to the next claim, the probability of a total of 3 heads in 6 trials is more than the probability of a total of 1 head in 6 trials. What do you think? True or false?
You said that having 3 is more likely.
Okay.
Because since it is half and half, like you're more likely to have a higher number than you are 1, but like you also could just have 1. But there's a bigger chance that you're going to have more than 1.
Right. Yeah, it's really weird because each event is technically an independent event, right? I flip heads or tails. And then I get a heads. Now the next time I flip, it doesn't have an impact that, oh, the last one was heads, so this one's going to be less likely to be heads. That's not how it works. It's still a 50% chance. So it's a really weird question to ask, right? But I do like the logic of thinking like six total trials. You have a 50-50 chance for the 6 trials. 50-50 chance each toss. Another way I think about it is if you were to create a tree diagram and you do the first toss, you have 50-50, and then the second one, it's going to branch off, you have 50-50. and it's going to create some different probabilities for us. So if I were to create a tree diagram of heads, and I have a 0.5 probability of that happening, and a tree diagram of tails, I have a 0.5 of that happening. Then I do a toss again, I have a probability of heads, and the probability of tails, and a probability of heads, probability of tails. My handwriting stinks. I'm going to do this a little cleaner. Let me zoom in on this for you. Just take my time. So, if we did our first toss, and we had our probability of heads, that's 0.5. And then we did our second toss, and we have the probability of heads, that's 0.5. Probability of tails, 0.5. And then we do the same thing down here. Okay, so just looking at it on my tree diagram, how many pathways are there where I get 2 heads on just 2 trials here?
1 out of 4.
Yeah, there's 1 pathway out of 4. And remember we talked about you would do 0.5 times 0.5 or 1/2 times 1/2, and that gives you the probability of getting double heads. We'll do heads. The probability of heads tails, there are 2 pathways, right? There's a 0.5 plus 0.5, 0.5. You can add those 2 pathways together. So you have a 50% chance of getting heads or tails. And then the last one, the probability of getting tails is there's only 1 pathway, and that's going to be a 0.25. So what happens is we have 1/4, 1/2, 1/4, and that all adds up to 1 after 2 trials. But what we'll see is the more trials we add, like the probability of getting 3 heads only, there's only going to be 1 path to get you 3 heads and no tails. There's only going to be 1 path that gets you 3 tails and no heads. And the same thing happens when you get to 6 heads. There's only 1 path that gets you to 6 heads, but there are going to be several that get you to 3 heads and 3 tails. So that's why the probability is going to kind of equal to be a little bit higher of getting 3 heads and 3 tails as you work through it, even though each event is independent. All right. This also leads to something called binomial distribution. And it basically says, in a sequence of independent trials of an experiment in which there are exactly 2 outcomes, there's success and failure, in this case it was heads and tails, with constant probabilities, the probability of success is that lowercase p, the probability of failure is going to be 1 minus p, basically the 100% minus the probability that you succeed. If x denotes the discrete random variable equal to the number of successes in trials, then the probability distribution function of x is, and then it gives you this whole thing. And this, to me, is what reminds me of the binomial theorem from last year. It looks a little bit different because the binomial theorem last year had a summation in it, but it still says, like, hey, you're going to choose 2 numbers and an x, and then you've got the probability of something happening to the x power, all right? And then you have the 1 minus the probability of n minus x. And x is an element of all numbers from 0 to n. So it looks very intimidating, but it's really not too bad. But the other nice thing is all we need to know how to do is we can summarize in words, x is distributed binomially with parameters n and p. And in symbols, it's going to look like this. X is distributed, so that's what this is right here, the distributed part. Okay, binomially, that's what the b is. With parameters n and p. All right. That's what this is saying here. And what we're going to do is we're going to look at what this means technically. So our first example today, example 22, says, hey, you have a multiple choice quiz. It has 6 questions on it. Each of the questions has 4 options, A, B, C, and D to choose from. If answers are guessed and X represents the number of correct answers, find the probability that you got 2 correct answers out of a total size of 6. So let's start with, for each individual question, what's the probability that you get it right? If like I'm on question 1 and I guess A, B, C, or D, what's my probability of getting question 1 right?
1/4.
Yeah, exactly. Probability of getting question 1 by guessing is 1/4. So what we can do then is we can say there are 6 questions total. So we can write this as our variable x, and then we do that sign that says distributed by binomially, and we're going to do 6, comma 1/4. And 1/4 stands for our probability here. Now, if I were to do this by hand, using this problem up here, the way this would work when I'm looking for exactly 2, I would say I'm going to do C of 6, choose 2. My probability is 1/4 to the x is squared. And then 1 minus 1/4 to the 6 minus 2. All right. That's what this looks like if I was calculating part A by hand. All right. So I'd still want to do, I could do 6, choose 2. I can do the factorial thing and set that all up. All right. But the nice thing is we can also do this in our calculator, and I'm going to show you how to do this in your calculator. So that'll be much, much easier than having to set this up by hand every single time. So bust out your TI-84s, and I've got these linked on our Canvas page. Let's take a look at example 23 here. For each situation, state if the random variable is distributed binomially. If so, find the probability asked for. All right. So first, is it a binomial distribution? And that basically means, are there 2 possible outcomes? Okay, that's what it's asking for. Okay. And then it has to be independent outcomes as well for a binomial distribution to work. All right, so part A says a coin is biased so that the probability of a head is 0.74. The coin is tossed 7 times. A is the number of tails. Find the probability that A equals 5. So again, this is indeed binomial because you have 2 outcomes. You have the heads and tails, and they're independent of each other. That's the key for binomial distribution. So for this one, you could say A is approximately, and then we'd say B. The total number is 7. The probability is 0.74. And then you guys are going to plug that into your calculator and look for the binomial PDF this time because you're looking for exactly 5.
Would you not be doing?
Sorry, what'd you say?
Would you not be doing x distributed binomially times 7 times 0.74 times 5.
Sorry, say that again. It was.
So we wouldn't be doing, like, you wouldn't, let me rephrase that. So you'd only be doing the two, like the trials and the probability, instead of also adding the x value.
Well, the x value this time is the 5, but you only do that part when you put it in your calculator. So yeah, so this is how we technically write it. I guess I didn't write it properly up here with the 2 and the 5 at the end, but that's just how it's written up here according to like the definition.
So if we like wrote it all the way out, it would still be like
it's fine. Yeah. So you're basically gonna go into your calculator now, and you're gonna do binomial PDF, and then you'll do 7.745. That's what you're gonna put in your calculator.
Okay.
Yeah, and then you'll get your answer. Okay, and again, these examples A through D all have the calculator example as well. All right, when we plug them in. So the probability of getting 5 heads, or I'm sorry, yeah, is it, A is the number of tails. So the probability of getting 5 tails with a very heavily favored die or coin for heads is pretty tiny. 0.0137.
I got 0.315.
0.315? All right.
So did I.
Oh,
Me too.
You know what? I know what I did wrong. Because the probability of tails, I gave you guys the probability of heads here. So how do we find the probability of tails? 1 minus 0.74. So we should do a 0.26 there in our calculator instead of a 0.74. That's my fault. Aha. And that should give us the correct value now. Sorry about that.
Can you write it out like how you would do it if you didn't have a calculator? Like how you wrote out like the equations above and stuff?
Sure. So what you would do then is you have this, and you're going to have 7, and you're choosing 5 of those numbers. Okay? And now what we would do then is we would say, oops, the probability of x, probability is 0.26. And we want 5 of those rolls to hit the 0.26. The probability of not getting x is the 1 minus 0.26, and we want 2 of those rolls to be that. This is the full written out version, but that's kind of what it looks like. But this right here only gives me the probability of 5. So what I would need to do then is I would also need to do the probability of 4, which would be 7 choose 4, and I would need to do this for 4. Oops. 7 minus 4. It's just like a summation like what we did in binomial theorem last year. I would need to do the probability of 3. I'd do 7 choose 3. I'd do the probability of 2. I have to do this every single time from every number below 5 all the way down to 0.
I thought you only had to do that when it was like x is less than or equal to 5, not just equal to. Do you have to do that regardless of
Nope, you're right.
the equal sign?
It is when it's less than or equal to. You're right. This one is just an equals to. So you're way ahead of me on this one. So.
Oh, so if it is less than or equal. Okay.
Yes.
Okay. All right.
Sorry,
I got it.
that's my fault. Yeah, if it's less than or equal to, we're going to do all of them. But if it's not less than or equal to, you're right. We absolutely only need to do this one. Okay? Yeah, but the less than or equal to is going to make it a pain. So this one, thankfully, you're right. We don't need any of this right now. But that's how we would write them all out, and we'd have to add them all together. And it would take a while to do it by hand, which is why I'm showing you how to do it in the calculator instead. Okay. Part B, a bag contains 12 white chocolates, 7 dark chocolates. A chocolate is selected at random, and its type is noted and then eaten. So the key here is we are not replacing the chocolate. It's eaten. So this will not work for binomial distribution. Because the odds keep changing every time. It's not independent event. So this is dependent on what happened last trial. So we cannot use this one, okay? Will not work for binomial distribution. And we can say the trials are not independent. So whenever you see that situation, that's when we know. Okay, whenever we see a dependent situation, that's when we know binomial distribution will not work. All right. A bag contains 10 red dice, 1 blue dice, and 7 yellow dice. A dice is selected at random and its color is noted, and then it's replaced. This is repeated 12 times. C is the number of yellow dice recorded. Find the probability of C is less than or equal to 6.
Wait, so if the sample number is changing, then it's not independent?
Yes, then it's dependent because it was dependent on the previous event. Because if I had 12 white chocolates, 7 dark chocolates, I pulled out a white chocolate and I ate it. Now I'm doing this experiment a second time. There's 11 white chocolates left and 7 dark chocolates. So all of my numbers have changed. So that's why it's not an independent event. This one, I'm replacing the die. So I'm going to pull out a die. Let's say I pull out the 1 blue die. I'm going to put it back in, so there's still 1 blue die in the bag when I'm doing this. Okay. So this one's repeated 12 times, so 12 is our total number. And we have to do some probability calculations here. So for example, the probability of red, we would have to say there's 10 red die out of 10 plus 1 plus 7. So 10/18. The probability of blue, 1/18. And the probability of yellow is 7/18. And that should all add up to 18/18. So that's the first part. And now we've got, hey, there's our probability of yellow. And we know that we're doing this 12 total times. Let's find the probability that we choose, a yellow at most 6 times. Okay. And that's how we figure out these numbers, and then we can go ahead and throw it in our calculator. Okay. Your homework tonight is going to be a lot of practice on these types of problems. Find the probability that we choose at most 6. Okay. And the order does not matter as long as we're just choosing 6 total yellow dice. That's the goal.
So we do the probability of 0 all the way up to so what is 7, 8? Oh, so we're doing yellow, never mind. Gotcha.
Yeah. All right, and then the last one, Sierra plays lottery in which the probability of buying a winning ticket is 0.001. E is the number of tickets Sierra buys until he wins a prize. So what's the probability of E is less than 7? Well, this one, it's like I don't give you a fixed number of trials. So we need a fixed number of trials in order to do these problems. So this one will not work. For binomial distribution. All right. All right, we've only got about 5 minutes left today. What I want to do is example 24. I'm going to skip it for right now. That one's got a calculator example as well. but it's very similar to the previous two examples. The last one that's a little bit different is example 25 here. And we're given this box in our textbook, which just is saying, hey, if we have this binomial distribution problem, then we have E equals n times p, E of x equals n times p, and var of x equals n times p minus, times 1 minus p. So this right here, E of x, is expected value. So if I ever ask you to find the expected value of something, you're just doing the probability times the number of outcomes. That's what NP is, n times p is. Number of outcomes times probability of that outcome, or the outcome we want. Okay. Now this next one, var of np 1 minus p, that's the variance. So if I ask you to find the variance, you're going to do the same thing as expected value, but then you're going to multiply it also by the probability that that outcome does not happen. That's the only difference between expected value and variance. So you multiply the number of outcomes times the probability times the not probability of it happening. Okay. Now this example says 2 machines in a light bulb factory are being inspected because quality control raised concerns. Managers have found that the probability the first machine produces a defective light bulb is 0.3. The second machine produces a defective light bulb is 0.2. Inspectors take the sample of 6 bulbs from the first machine and 5 from the second. So it gives you use these numbers to model the number of defective light bulbs in the samples from the first and second machines respectively. So compare and contrast the central tendency and spread of these binomial distributed random variables. All right. So first thing we can do is we'll say, let's look at expected value. So the first one was X, and we're going to say there are 6 light bulbs and the probability was 0.3. The second one, we'll say was Y, and there were 5 light bulbs and the expected value is 0.2, or the probability was 0.2. All right. So when we do 6 times 0.3, we should get 1.8, I think. Yeah. And we do 5 times 0.2, we should just get 1. So we're expecting one of our light bulbs in the second example to be defective. We're expecting 1.8, almost 2 light bulbs to be defective in the first one. Okay. And then what we'll do with the variance is we will say we're going to do the same thing where we do, whoops, if we're doing the variance of X, we'll do the 6 times 0.3, which is that 1.8, times 1 minus 0.3. And that's what we do for the variance. And the variance of Y, 5 times 0.2 times 1 minus 0.2. And that's how we identify our variance respectively for each problem here. And we get a variance of 1.26, 5 times 0.2 times 0.8, we get a 0.8 variance.
I don't know if this is just me, but I'm kind of feeling like I need a day where we just kind of like work on homework in class because I'm feeling really confused.
Sure.
On a lot of it.
Okay. No, I mean, I get that. We're going really fast right now.
Yeah, and I'm kind of having a hard time like getting all these assignments done because I just don't understand how to do some of the problems. So I think it'd be really good if we like had a day to work on that.
Okay.
Other than office hours.
Other than office hours, yeah. Okay. So let's see what we can do here then. So how about on Thursday we can just take a day then? We'll take a breather on Thursday next class. and we'll see if we can get caught up a little bit. And let's do that tomorrow. Tomorrow we'll do that. Tomorrow's Tuesday. So tomorrow we'll take a day, we'll get caught up on this. I'll make this assignment due on Thursday so we can answer questions for it. And on Thursday we'll do section 7.7, which is the last section of this book, this chapter.
I have questions on like the past like
4
homework
7. That's fine.
assignments.
So we can go over any homework questions we want tomorrow in class. We'll do that. So tomorrow we'll make it a homework question review day, and we'll see if we can get caught up. Make sure we're feeling comfortable with this material before we move on to the last section of the chapter. How's that sound? Does that work for everybody?